Okay, in the first section we introduced the idea of a statement, simple statement, and then we talked about these logical connectives, the way we form compound statements by combining simple statements with words like and, or, not, if, then, a couple others. So what I want to do in this section is take those ideas and formally define them. So here's a slide from the 7.1 notes. Just these are these 6 logical connectives that I introduced without actually really formally defining them. What I mean by defining them, oh, and just one more thing, remember this this symbol for not is sometimes used, I think our book uses it's kind of wiggly, the tilde. So if P is a simple statement, then this means not P. Okay, so I just want to go through these one by one and define them. And like I said, defining them means just formally putting down how they work. What happens when you combine 2 statements into one using one of these logical connectives. Okay, so first one is the negation. This is the only operation that's what's called unary, meaning it acts on one single simple statement. So remember, P is a statement, so if P is a false statement, then not P is a true statement, and if P is true, then not P is false. The next logical connective we talked about was the disjunction, or the or statement. And so basically this idea of a truth table, like this chart right here is what we call a truth table. It basically it's sort of set up like this. It's a sort of like a T chart, and on the left we have the simple statements, and on the right we have what happens with this compound statement. So if we take 2 trues and combine them with disjunction or true equals true. Or if we take a true and a false and combine them with an or, the result is the overall compound statement has a truth value of true. So these are like this is a definition. This is how we define the operation of or. One of each in either direction, true, false, false, true, either way, true, or false or true equals true. And with a disjunction, with an or statement, the only way to get a false is to combine 2 falses. So false or false equals false. Now, one thing we talked about when we covered the first section was that sometimes words in the way we use words in conversational English is different than the way we use them mathematically. So for example, mathematically, a disjunction is true if the first statement or the second statement or both statements are true. But conversationally, that's not always the case. So an example first example that came to my mind was, you're out having dinner, someone's waiting on you, they say, would you like soup or salad? Oh, not of. Yeah. Would you like soup or salad? So the implication there is, you could choose soup, so soup could be true and salad could be false. You could choose just salad, so soup would be false, salad would be true, but you can't choose both. So you can't have both of them be true. You can if you pay extra, but for the price on the menu, you can't have both. So this is just an example of where, or in conversation and or in mathematical logic don't work exactly the same way. The third logical connective we talked about was the conjunction, or the and statement. So, and again, this truth table looks like this. We have our simple statements, P and Q, and then our compound statements, P and Q. With a conjunction, when you combine 2 statements with a conjunction, the only way for the and statement to be true is if both simple statements are true. So true and true equals true, Otherwise, each of these cases is false. So what we're doing here, on the left, we're examining all possible combinations of T's and F's. So if we have two statements, P and Q, and this goes back to chapter 3, to the fundamental counting principle. How many different combinations, or how many different sequences of trues and falses can there be? Well, there's two options for the first statement, two options for the second statement. The fundamental counting rule says multiply those two numbers. 2 times 2 equals 4. So we get these four. What am I doing? We get these 4 rows in the truth table definition. The next logical connective is the conditional, or the if-then. So now the if-then works a little bit differently. So be careful here. So in the second row, if P is true and Q is false, then the conditional statement is false. But if P is false and Q is true, the conditional statement is true. So with the disjunction or the conjunction, one of each work the same whether the true came first or the true came second. Here, the conditional statement is true only, or the conditional statement is false only in the case where the true statement is the if and the false statement is the then. Excuse me. The way I think about this one is the conditional statement, if-then statement, is false when it can be considered a lie. So let's say I make this statement: if I'm elected, then I will lower taxes. So this is my P. I'm elected. And this is my Q. I will lower taxes. So if you think about those 4 rows of the truth table, so true, true, let's say P and Q. So this is P, this is Q. So when P and Q are both true, so yes, I am elected and taxes go down. All right. I kept my word. I did not lie. But in case 2, what would that be? If P is true and Q is false, that means I am elected, true, taxes don't go down if Q is false. So that would be the only case where, so this was true, true, I'm elected is the P, I lower taxes is the Q. So I'm elected, true, taxes don't go down, I don't lower them, false. So here in red, this is a lie. So if I'm not elected, what happens over here doesn't have anything to do with me, right? So if taxes don't go down, if I wasn't elected, you can't put that on me. I didn't lie. I said if I am elected, then I will lower taxes. So case 2 is the only one that where we would consider the conditional statement a lie. Let me just go back a couple of slides. So that would be I am elected, true. I didn't lower taxes, false. Therefore, I lied. That's the case where the conditional statement is false. And the conditional statement's a bit more confusing than the other two. There's other ways you could phrase an if-then statement. There's actually at least 10 different ways. I'm not going to cover that here because it's not relevant for the homework. I'll go through this very quickly. So both of these statements are conditional statements, but they're not written in exactly the form like if something then something. We don't have both words if then. So here in this first one, I go to the beach if it is sunny. The second one, I go to the beach only if it is sunny. Now these sound pretty similar, but mathematically they mean two very different things. So just like I did, let me just go back a couple of slides. Just with this conditional statement, I identify the P is the I am elected, and the Q, I will lower taxes. So every conditional statement or every compound statement has at least two simple statements within it. So these two statements about the beach, I go to the beach and it is sunny. So one of these, I go to the beach, it is sunny. One of these is the P, the statement that comes first, and one of these is the Q. The question is which one? And then the same thing in the second question. I go to the beach. So the same two simple statements, it is sunny, but in this first case, I go to the beach if it is sunny. That means I go to the beach on every sunny day, but that doesn't mean I can't go to the beach on days where it's not sunny. So, hint, for each determine whether I could be at the beach in the rain. Well, yeah, here I can be at the beach in the rain. I go every sunny day, but I could also go other days. In B, well, this definitely means something different, because this second statement means that I cannot be at the beach on a rainy day. So if we reword this into the formal if-then form, in this first statement, the it is sunny becomes the P, and in the second statement, the I go to the beach becomes the P. Well, like I said, this is not going to be on the exam, so don't worry about this so much. So these are, and you could spend some more time with this if you want on the PowerPoint file, but these are just some of the other ways that an if-then statement could be stated. So the standard form is if P then Q, but all these others mean the same things. Or it could be reworded into the form if P then Q. And then the last logical connective is the biconditional, and this is the conjunction of two conditionals. So what that means is if you have the P implies the Q and the Q implies the P, and they're both true. So you have both directions of the conditional. We have the biconditional. So for example, if a number ends in 0, then it is divisible by 10. So the ends in 0 implies it's divisible by 10, but also if a number is divisible by 10, then it has to end in 0. Ends 0. Okay, so a biconditional is basically a conditional that goes both ways. And the definition of the biconditional, the truth table definition of the biconditional, well, we could use things we already know. So symbolically, the biconditional is the conditional forwards and the conditional backwards. So if we want to construct a truth table, now this is one of the three questions that you will see on the exam, is to construct a truth table like we're about to do here, using two simple statements, P and Q. Okay, so construct a truth table for this. Okay, so what that means is take into account all the possible orders of true and false that we could have, false and false, and to construct a truth table means to take this compound statement and figure out these four truth values. Now, rather than do this in one step, there's three operations here. So three operations, we should do this in 3 steps. So let me get rid of this, and this. So let's just focus on this first. We'll do this first conditional statement. Now we have the definition of the conditional. If, and let me just go back to real quick, back to here. Okay, so this is our definition for conditional. This is how conditional works. If you take, two trues and combine them, you get a true, and so on. So we're using this definition to solve this problem that we're currently working on. So by definition of the conditional, that's true, true false equals false, false true equals true, and false false equals false. And then the next, so we'll work inside the parentheses first. So the next logical connective, we'll do this one second. Q implies P. So here the Q comes first, so we're going in this direction. We're taking the Q column and the P column, and we're going in this direction. So true first, true second, that will be true. Now down here, false first, true second, that's also true. Down here, true first, false second, that is false. And down here, false first, false second, that is true. All right, and now the third logical connective, we have definitions for all of these. So now we'll use the definition of the and, definition of the conjunction. And now what are we doing? We are, let's get rid of this. Now we're taking, for this, what I just highlighted in green, for the and here, we're taking this column, which is this. We're taking this column, which is this. And we're combining them with an and. True and true, false and true, true and false. False, oh, sorry. This should be true. I think I may have said true, but wrote false. Okay, so we're taking these two conditionals, combining them with an and. So in this first case, true and true. So now this last column is for the whole statement. We're taking this P and Q, or P implies Q, and Q implies P. True and true equals true, false and true equals false, true and false equals false, and true equals true. So when you're constructing a true table, one column at a time, one for each operation, and this last column is your final answer. This is what you would type into Connect Math. So our definition of the biconditional is given by this truth table that we just came up with on the previous slide. This is basically all the definitions. I left this one out because it's not in the textbook. If we met for class, it would have been something we would have talked about. But negation, conjunction, disjunction, conditional, and biconditional. These are the 5 logical connectives you'll see in the homework and on the exam. So this slide, slide 21, this is something you might want to have handy. You might want to write this out or print it up. You want to have this out when you're taking the test. Okay, next we could, based on those definitions that we just established, we could look at the truth values of compound statements now. So this is an example of a this one's a tough one. I don't want to say simple or compound. It's actually a compound statement, but because this contains a universal quantifier. But that's not what's important right now. Just consider the truth value of this statement. All grass is green. In this case, I would say this is a false statement. All grass is not green. Some some grass is brown if it's dead. I actually lived in Kentucky, and some people say, there's bluegrass. Some places in Kentucky it's called the bluegrass state. Anyway, so now let's look at three simple statements. Well, three statements, not all simple. So all grass is green. Okay, we say that is a false statement. Q. Not all people have green eyes. Yeah, that's true. Not everyone does. The Earth is shaped like a cube. I would say false for sure. Okay, so now we have three statements, and we have the truth values of these statements. So what happens if we combine them into a big compound statement? Okay, so for example, like this mess down here, like, is this true or is this false? You only have two options. The overall truth value of this messy compound statement, it's got to be either true or false based on the values of these statements. And we said false, true, and false. And so the way we identify the truth value of a compound statement is, plug in the values of the simple statements and apply all of those logical connectives, all of those rules. Okay, so what I'm going to do is, this is a Q, and instead of Q, let's plug in the value of Q. And in logic, the values are either a true or a false. So the value of the statement Q is true. And let's just go through and just plug in all those T's and F's wherever those statements are. So R, we're not going to worry about the negation yet, just the statement itself. So R is a false statement, so we'll plug in a false there. This P is false. This R is false. Let's see, P here, so that's another false. And this R over here is another false. Okay, so now let's do, okay, yeah, so this basically what I just wrote in with my pen is this. So now let's simplify this just one piece at a time. All right, so this not false has to be true, and so we have true or true, and by definition true or true equals true. And we've got an and there, not, and some parentheses, and this false or false is a false, and this false and false is a false, and then we've got this conditional here, so it doesn't have to be done in one step. So now let's see, what's this? False implies false. Going back to the definition on the true table, false implies false is true. So we have, so now we're left with true and not true. So true and not true, that's true and false. And by definition, true and false equals false. So the overall, based on these three values, the overall truth value of this statement is false. This is the second one that you'll see on the final, but you will see one much smaller than this. It's not going to have all these different, 6 different logical connectives. Just it'll be basically just, you'll be given a couple of statements and a small compound statement, and the question will be, what is the overall truth value of that compound statement? Right. And constructing truth tables, this is what we did for the biconditional. So we've already pretty much covered this. Actually, probably could have gone through some of these slides earlier. So this is what I said. Excuse me. When we were doing the biconditional truth table. The truth table is basically a T-chart where you have the atomic statements or the simple statements over here, the P's and Q's. Could be 3, could be 5, it could be PQR, PQRS, just depending on how many simple statements make up the one compound statement. So this overall truth values is one single column of just T's and F's. So let's say make a truth table for this. We have two simple statements, so there's a P, there's a Q, and those simple statements could be both true, could be P true, could be just Q true, or they could both be false. So what happens to this compound statement? Well, this compound statement has a negation in there. So what are the values of just the not P? And so if we have P here, then the values of not P would be the opposite. False, false, true, and true. And now to apply the AND, let's say not P and Q. Well, now where are we looking? We're looking at the not P column, we're looking at the Q column, and we're combining them with an AND. So now we look at the definition of how AND works. The only way the AND will be true is if both statements are true. So here there's a false, so false, two falses make a false, two trues make a true, and one of each makes a false. All right, so this is the final answer. These are the overall values of the compound statement. And now the last problem that you'll see on the final is another truth table. So basically two truth tables on the exam, and one of them is going to have three simple statements, P, Q, and R. So if you think back to the last problem we just did, all right, we solved this one and we got false, we got false, false, true, and false. But before we did any of this over here, the first thing is we set up the truth table over here. So all the possible combinations, according to the fundamental counting principle, 2 times 2 is 4, so there's four rows. Now, if we had a third statement, there's 2 options for the R as well, so you have to add, you'll end up with 8 possible sequences of trues and falses. So if you think about like what happens with just this first row, TT, P is true, Q is true. Well, this could be followed by either a Q, if there's a third statement, R, it could be followed by either a true or a false. So consider this statement to find the truth values of this statement. Now we have a P, a Q, and an R. So if P and Q are both true, well, now you have 2 options for the R. R could be true or R could be false. So these are both true, R could be true, or R can be false. So you're basically taking each row of the 2-letter truth table splits into 2 rows, so the 4 rows become 8. If P is true and Q is false, R could be either true or false. If P is false and Q is true, R could be either true or false. And if P is false and Q is false, then R could be either true or false. And when we're setting this, when we're doing this truth table, well, we have 4 logical connectives here. We have an and, an or, a not, and an if-then. So we'll have to see what happens to each one of those one at a time. So there's a not R up there, so we need a column that tells us the values of not R. Then we've got this Q or not R, so we'll need a column for that. So I could do this one first, this one second, inside the parentheses first. So this one third, that's a 3, I promise. So there's a column for P implies R. And then finally, outside the parentheses, we could do the Q or not R column and the P implies R column. All right, so the way this works is just okay, so let's see. If we have the values of R, we have the values of R here, so we're using this column to do this. Okay, so if we have the values of R, the values of not R would be simply the opposite, so false, true, false, true, false, true, false. Oh, oops, sorry, again, this should be a false there. I think I said false but wrote true. False, true. All right, now to the next logical connective. Now for the, all right, so first we did the not. Now here we're doing the or. So for the or, we are taking the Q column, which is here. We're taking the not R column, which is here, and combining them with an or. So with an or, one true makes the whole statement true, so that looks like a true, a true. Here we have two falses, so that's false. False true will give you a true. True false is a true. Two trues is a true. Here again we have two falses, so that's false, and a false true makes a true. And then moving on, we have the conditional here. Okay, so we're taking, with the conditional, we're taking the P column, and we're taking the R column, and combining them with a conditional, with an if-then. So remember, with a conditional, the only way the conditional is false is if true comes first and false comes second. So right there, there's a false. Right there, there's a false, true, false. And that's it. Everywhere else, true, 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 true. Okay, so that looks like it'll be true. Second one is false. Third one is true. Fourth one is false. And the last four should all be true. All right, and then moving on to the last logical connective, the and. So this and, we are taking the Q or not R column, which is here. We're taking the P implies R column, which is here, and combining those two columns with an and. So remember, with an and, two trues make a true, everything else is false. So that's true. The second row gives you a false. The third row, false true, will be false. True false will be false. So that's a true there. That's a true there. Another true here. That's a false, and that's another true. All right, so these are the final overall truth values of the compound statement given any combination of P's and Q's. All right, so, and if you, you could see this on the PowerPoint file that I upload. Basically what we just did on this slide, this is the initial setup before working it out. Okay, that about does it for section 7.2.